So in this case, we are going to consider as part of our wind power generation, the calculations which are necessary as we are to consider this topic of renewable energy systems. Remember, before I referred that we are going to need to harness the kinetic energy, all right, which is used to generate the electrical power. At the end, we are going to have the electrical power. So as part of our calculations, we need the calculations of the kinetic energy of the wind and also the power of the wind. But these calculations, they are also influenced, or they are affected by so many factors, which include the size, the design of the turbine. The design and the size of turbine is included. The air density, the height of the turbine, which is the hub height. The height of what? Turbine. Which goes hand in hand with the velocity, as I talked before, as I referred this before, that these two, they work hand in hand. Where the height is, the velocity is. So you must consider these aspects as part of your calculations. All right. So let us start on the calculation based on the kinetic energy, as the kinetic energy will give us the power. We do understand that the kinetic energy gives us the power. So let us start with the kinetic energy. So that is the kinetic energy of the wind. So the kinetic energy of the wind, you can just write EK like this, and you can just even write wind if you want, or you can just indicate with a small letter W for the wind, all right, as we are referring to the what? To the wind. So it follows that the kinetic energy of the wind can be determined. Guys, we do understand kinetic energy of mv squared. So it is the same thing. Same calculation as we do understand our kinetic energy from our engineering science. So that is half mv squared, meaning to say we are considering the mass of the wind and the velocity of the wind. Kinetic energy, we are dealing with energy which is measured in what? In joules. So that's the M representing the mass of the wind. All right, so you're going to consider mass of the wind measured or taken in what? In kilograms. The V representing the velocity or the speed of wind. This is velocity or the speed of what? Of the wind. So as we consider the speed, velocity in what? Meters per second. So that's we've got the kinetic energy. So the mass must be considered, velocity also. Then we also consider the power, which is now generated, the power of what? Of the wind. Power of the wind. So just gonna write this as P wind, or just PW for wind. Okay. So this wind power, or the power that is generated, can be determined. Remember, before we talked about the relationship between the velocity, Remember when we refer to the velocity and the power output of the wind, right? They will be having the velocity and we had that exponential function. And I say that power can be determined from there. So it follows that the wind power can be obtained from half of the mass rate times velocity squared when given the mass rate. Take note, the mass rate when given kilograms per second, we can use this formula. But sometimes they can give us the density of air. Remember these aspects, the air density. When the air density is given, it therefore follows that the wind power can be determined from the formula of the density times the area times that velocity to the exponent of 3. So this part here, the density, the area, and the part of the velocity was, as we can see, there's the velocity, it was to the exponent of 2 there. So it follows that this mass rate, when substituted or when replaced there, it is simply mathematically here, it is simply this part. If we see this part, it was like this. Half of the mass rate, it simply means it represents density times area times velocity. This part here, it represents the mass rate times v squared. So that is where we are having at the end the v times the v squared, which is giving us v to the exponent of 3. So this part here is the mass rate. So meaning to say, as you are calculating the wind power, as we do understand, guys, power measured in what? In watts. So it's going to depend, is it taken per unit area? When you are calculating power per unit area, as we understand this, guys, from our power machines N5, anything per unit area, per unit mass, per unit volume, it will be the power, which means in watts per unit area per square meter, whenever you are given for area, which is taken as 1 square meter, it means take your area as per unit area. Per unit area. A square meter, it's per unit area. All right. So let me just write this. I'm gonna go back here to the mass rate. Let me finish this one. So whenever the area is given as 1 square meter, it's per unit area, that one. When given 1 square meter, whenever the area is given as 1 square meter, the power, which is the wind power, must be in what? The unit for power per square meter, meaning to say watts per square meter, depending with your conversion. Are you going to convert to kilowatts? It is up to you. You can write as kilowatts per square meter, per square here, per square. Remember, area per square of the area. So you can convert to kilowatts. It is up to you, but as long it is per square meter, per 1 square unit of area, which is the swept area of the turbine, this A that we are referring to. All right, so let me just rev it here. So this A represent the swept area of turbine. This is the swept area. Swept area of turbine. which is to be taken in what? In square meters. But like I said, whenever the area is given as 1 square meter, that's where you calculate your power as per square unit of the area. But when you are not given that, you are given a certain value, you calculate your exact power as it is. Or maybe they give you the radius, or maybe the diameter. Therefore, you calculate your swept area from there, from the radius, pi r squared, when given the diameter, pi d squared over 4. In meters, the radius or the diameter must be in meters for us to obtain what? Square meters. So sometimes you are not given that. You have to calculate that area. All right. We also have the density, which is also part of our calculation here. So this is the air density, the density of air. So you can even write density air here. It is up to you, but that density is for air. So this is density of what? Of air, which is measured or taken in kilograms per cubic meter. So we are going to talk about normal consideration of that air density on its own. All right. But for now, let's just know that we have got the air density there. Then the V representing the velocity or the speed of the wind as mentioned before. All right. So these are the basic calculations. And like I said here, this whole part represents the mass rate. So they can ask you to calculate the mass rate given the density, the area, and the velocity. We have got the mass rate from there. All right. So I want us to have this extra part of the calculations. Just as we have got the power, let us also consider the calculation of the mass rate. So you can just simply take it from the formula that we had from the power. We can see that the mass rate is equivalent to the density of air, the swept area of the turbine, and the velocity of air. So that is density times area times the velocity. All right. So this gives us the mass rate, as we do understand, in kilograms per watt per second. So guys, we have got everything. We talked about this, the density of air, the area, the velocity. All this is from what? From the air. So that is just a repetition, and also the calculation of area when you are not given, where this represent our mass rate, which is taken in kilograms per second. We also have to consider the air density, all right, and as a separate part. Let's just say as a separate part. But we already talked about this or referred to this part of the air density, as we have got this on our calculation. Air density was there. So it simply means we already have this one. But what exactly are we referring to? The density of air is influenced by the temperature, pressure, and humidity. So air density refers to the mass of air per unit volume. All right, mass of air per unit volume. So if that is the case, we are referring the mass of air in kilograms per, that is per unit volume. The units of volume, what? Cubic meters. So therefore density measured as what? In kilograms per cubic meter. So basically at sea level, we are going to see or notice that the density of air must be 1.225 kilograms per cubic meter, on a condition that, because the density is affected by what? Temperature, pressure, and humidity, remember. So at that influence of the temperature and pressure, our temperature must be 288 Kelvin, meaning to say we are talking about what? 15 degrees Celsius. At a pressure of 101.325 kilopascal. At these two conditions happening at the same time, simultaneously, the density of air is supposed to be 1.225. So when we are not given that, we have to calculate it from pressure and temperature. But in most cases, you will be given that density of air. But when we are not given now, how are we going to calculate this air density? Remember that pressure is equal to density. All right, pressure is equal to the density times the gas constant times T. We had this part of calculations, I think, in our engineering science, yes, science and form. So from that formula of pressure, let us have the density as the subject of the formula. So it therefore follows that density is equal to the pressure over what? RT. So when we are not given the density, it can be calculated from this formula. It can be calculated from there. So we already have our pressure. So if you are using pascals, it affects the value of R there. If you are using kilopascal, again, it affects our R. Our R will be taken now in kilojoules. So it will be actually our R there for air is 0.287 in kilojoules per watt, per kilogram Kelvin. So you must be careful. When you have this one in pascals without a kilopascal, then this one, we must not have the kilo there. It means you will use 287 joules per kilogram Kelvin when you take your pressure in pascal. But when you use the kilopascal, therefore use your R in what? In kilojoules. That is the concept. So anyways, guys, we know these units, conversions, and use of units. So the R there, that is the specific gas constant. This is our specific gas constant. All right, then we have got our temperature, our absolute temperature in what? In Kelvin. So there we have got our absolute temperature. All right, which is measured or taken in what? In Kelvin. So remember your conversions from degrees Celsius to Kelvin when it is necessary. So this part is important as we are going to consider our calculations. We also need to understand the average wind velocity. All right, average wind velocity, as it is on its own. This one, guys, it is saying on its own average. Whenever we're calculating average, you sum up the two, you divide by 2. So there must be the initial and the final. so that average velocity can be determined or can be calculated. So it therefore follows that the average velocity is simply the sum of these two. Then we have to divide by what? By 2. Okay. So that is what we are going to have as the average velocity, which is taken from the conditions of the streamline, where we are given the wind streamline through the turbine. All right, just like when we are dealing with those nozzles like that, you'll be having where it is entering, then we also have the exit. So there we're going to have the velocity at the initial, the area, also the mass rate, the same thing, V2, the A2, the mass rate at the exit, where in this case, in between, we shall have the part of the swept area. So those conditions are going to be considered. There are some of the laws that are going to be considered later on as part of our calculations. We are going to see that one later on. Then, as part of your calculations, remember I was saying before, where the velocity is, it corresponds to the height, the velocity and the height. When you're dealing with a turbine, the height of the turbine, velocity above the ground level. So those velocities now, they are affected by the land surface roughness, or the factors that are of the landform factors. All right? Whenever we are to consider the calculations of the velocity. So let's consider this part of the land surface roughness. Okay? And height factors. So in this consideration, we are saying as we are to have a power plant, which is the wind power plant. Remember, we referred to the installations or the way we are going to have these plants in terms of the land where it is situated. So these are going to affect even our height, the height factors and velocity. The wind speed depends on the roughness of the terrain and also the height of the hub, the roughness of the terrain. So with that roughness, we have what we refer to as the friction factor. The friction factor, which is due to the roughness. The friction factor. The friction factor is taken according to the land surface roughness, according to the landform, taken or used according to the landform or the land surface roughness. The land surface roughness. So this is going to have an effect on our calculations and also the height. So it follows that V over V naught is equal to H over H naught, everything to the exponent of alpha, which is the friction factor. So this formula simply states that the V that we see on top corresponds with the height that we see on top, which is at a given distance that is, we have that height of the turbine or the hub height. At that turbine height, we have the corresponding velocity. So we are simply saying V is the wind velocity at this height h, at a height h, as it corresponds, which the height h is representing the height of the turbine. Height of turbine, which we can just be given in short as hub height. Okay. So whenever we have got this V, it goes hand in hand with H. These two, hand in hand. Whereas the other velocity that we are given of the wind, this one, goes hand in hand with this height. And what does that height represent? It is simply the height at ground level. So we are going to notice that V naught goes hand in hand with H naught. So this is the wind velocity at a height which is referred to as what? As H naught. Again. So they work hand in hand, or they are to be taken hand in hand. So when we have got this velocity, we are talking about this height. And that height is simply the normal, it is just a normal height that H naught is just the normal height that we have, the normal height above the ground level. Above ground level. That's just a normal height above ground level. And we referred to the what? Friction factor. Taken according to the landform, which is the land surface roughness. So we have got also to consider the friction factor. This one is just a constant. So remember, guys, the units as before, as we consider the wind velocity measured in what? Meters per second, as we consider the height in what? In meters. The velocity, meters per second, the height in meters. But the friction factor does not have the unit. It is unitless. It's a constant. It's a constant that is taken according to the land surface roughness. So these surface roughness or the land friction factors due to the land surface roughness can be given. You are supposed to be given actually those values. Unless maybe they want you to play around with everything there, then you can you have that one as change of subject. But in most cases, you are given that and you just have to substitute. But just for the sake of revision, these are some of the factors that we are going to need as part of our syllabus. The land friction factors, all right, land friction factors according to the land form that you are given, to the roughness of the land. So let's just have the land form. All right, then the friction factor. The friction factor. So like I said, you'll be given these ones. you'll be given these ones, but just for the sake of revision, you might need to know some of the basics according to your syllabus. We have the type of landform, which is smooth hard ground. Smooth hard ground. On this one, the friction factor is to be taken as 0.1. So like I said, guys, you will be given these values. All right. Then we also consider on a landform where there are tall grasses on level ground. So you can have tall grass on level ground. On level ground. So this one is 0.15. All right. Then we also consider where we have got, all right, number 3, where we've got tall hedges. And we have got some shrubs there and some crops. In that case, we can use 0.2 as our friction factor. So it is affected or influenced by what? The landform. What is it that we are having there? It is going to affect the friction factor. We also have conditions where we are dealing with the forest. 0.25 for that one. All right. We also have conditions of villages with gardens and trees. All right. Let's say we are in the village. So we have got villages with gardens and trees. So when we are given such type of a landform, approximately that will be 0.3. And we also have conditions of cities with tall buildings. Cities with tall buildings. They do affect the issue of the friction factor. So as we can see, it is a major issue, the landform. Where are we going to situate the wind farm or the power plant? We talked about that class. So you see now it is because of that. The friction factors, they differ according to where we situated that, the landform that you are dealing with. So these are the factors that we are going to use when we are dealing on the calculation of the velocity, where we have got the land, surface roughness, and height factors, which are considered mostly on the calculation of what? The velocities. All right. Then the last part, as we consider the wind electricity generation calculations. This is on what? Wind electricity. They can just give you the ratio between powers. So the ratio between powers is just, guys, as you do understand, just like output and input. So in this case, P ratio is going to be, the output is the, you'll be given two conditions because you have got two velocities, remember? So you calculate the first one, we're just going to call it P wind 1, and another one, P wind 2, due to the different velocities. So the two powers that we have will give us the ratio. So that is P wind 2 over P wind 1. To calculate these powers, we talked about this, how to calculate these powers depending with the information that you are given. The power of the wind can be calculated, remember, but there will be different according to the what? Velocity. Now, that is where we talk about that issue of the roughness factors and the height factors there. All right. So it gives us a ratio between the given powers. As long as we deal with output and input, we also have the power that is absorbed by the rotors. Power absorbed by the rotors. Meaning to say we are referring to the rotor power. When having these two, the rotor power can be calculated as the difference, which is P wind 1 minus P wind 2. That is the rotor power. And also, sometimes they can ask you to determine or calculate the efficiency of the rotor from that rotor power. You can also calculate the efficiency of the rotor as output over the input. So the output is the rotor power, whereas the input is the wind power 1 as we have it, P wind 1. So that is the consideration. So the rotor power, it is just the output at the end of the day. So efficiency can be determined as a percentage, just multiplied by 100%. All right. So these are some of the basic calculations we shall add as we move on. It is just direct calculations indeed. You just have to go through as many questions as you can, because this is like something new to our syllabus. So the more questions that you work with can be better, so that you understand how are they going to ask these typical questions in your final examinations.